Our topic is what is displacement current. Before going into the details of this cause of this current, let us first note the physical mechanisms involved in the current flow in a circuit comprising of pure conductor where Ampere's law is valid, and also in a circuit comprising of conductor and dielectrics or any vacuum place where modified Ampere's law or Ampere-Maxwell's law is valid. Now we have to explain the cause of displacement current from the idea of Maxwell. Therefore, from the conventional classical processes of current flow and as per the validity of Ampere circuital law in electricity, the total current density through any pure conductor may be considered as the summation of due to four current components mainly. This is due to the free charge carrier motion, and this is the dielectric polarization current density, and this is the magnetization current density, and finally the convection current density due to the motion of the circuit as a whole. Now, neglecting the convection currents in a static circuit, the expression may be simplified as where Jt correspond to the total current density, and this is due to the free charge motion of the free charge, and del P del T is the variation of electric polarization vector inside the material, and P is the dielectric polarization vector. So it corresponds to the polarization current, and this is the magnetization vector inside the circuit material elements, and the curl of M contributes the magnetization current. Therefore, the three main Ampere's currents components may be considered as J free, as this current is due to the flow of free electrons or holes or ions in a circuit, and del P del T that corresponds to the polarization current, and this is due to the space-time value of molecular currents caused by a varying polarization, and finally the curl of M, that is contributes the magnetization current, is due to the space-time variation of magnetic dipoles or where there is inhomogeneous magnetization. Now, in electrical circuits, to assure the conservation of charge, it is necessary that this total current must obey the equation of continuity, the equation 2. Thus, taking the divergence of the total current as per Ampere's current of our equation 1, we get the equation 3. Now, substituting the value of divergence of J t in equation 2, we may write the equation of continuity like this, and it is numbered as equation 4. Now, from Gauss theorem in vacuum, we know that the divergence of electric field in free space is related with its charge density by this relation, very important relation in electrostatics, and where epsilon naught is the permittivity of the free space. Now, taking the time variation of this expression, we get del rho by del T equals epsilon naught times divergence of the rate of change of electric field in free space. Now, substituting this quantity in our present equation of continuity, we get the equation like this, and del rho by del T here replaced by this quantity, and we get the equation 5. Now, adding these two terms, that is divergence of del P by del T with this quantity, that is the most important quantity, del E by del T, that is the variation of electric field in space with time, we get the equation like this, we termed as equation 6. Now, equation 6 we may write also in this form also, where D equals to the polarization vector with the external electric field vector times epsilon naught, and in free space the polarization vector will be 0. In that case, displacement vector will be this term only, and from equation 6 we get the divergence of total current, that is including the new current component due to the rate of change of electric displacement vector is equal to 0 in our present case, and we write as equation 7. Therefore, the divergence of total Ampere's current from equation 2, as I told in my initial consideration of Ampere's total current, that is the component of magnetization current, and this is the polarization current, and this is the free space movement current due to free space motion. And here we note that the divergence of this total amperes current is not equal to 0, and therefore the total amperes current is not sinusoidal. However, from equation 7, the quantity, that is this total current quantity in our present discussion, including the rate of change or displacement vector, which also we may write as the amperes current with additional current component due to the variation of electric field in free space with time, is sinusoidal, because the divergence of this total current equals to 0. Therefore, in any electrical circuits having dielectrics or vacuum places, just like as an example we consider a capacitor, we adding the term epsilon naught del E by del T, the variation of electric field with time in free space, the new component of current to the amperes total current is a solenoidal. The need of the above term was first recognized by Sir Maxwell and named as vacuum displacement current, and does not have the significance of a current in the sense of motion of charges. Thus, the total amperes current with the additional current component, that is termed as displacement current in vacuum in our present case, is solenoidal. Where there is a change in electric field due to the accumulation of charges, as in a capacitor, the current is continuous by the displacement current in spite of the physical discontinuity in the complete circuit. Now I want to reconsider the role of capacitor in a simple AC circuit for simple understanding of the displacement current. Now we consider this circuit like this, where C R equal to resistance of the circuit, C is the capacitance value, and Vt is the voltage of the AC sources, it is the electric field, time varying electric field inside the capacitor plates for the AC voltage, and these are the associated magnetic field for the AC current through this circuit. Now the voltage by distance is equated as the electric field inside the capacitor plate, and I is the current, that is dq by dt through the capacitor, where q is the charges accumulated on any capacitor plate, and the value of capacitance may be calculated from this relation, that is epsilon naught A by D, where A is the cross-sectional area of the capacitor plate, and D is the separation between the two plates of the capacitor. Therefore, the current we get from dq by dt, where q equal to Cv, and considering C is a constant, that is C times dv by dt, and putting the values of V from this E times D, we get the value C d by dt, where we consider that D is a constant. Therefore, the current we get the putting the values of capacitance, we get like this, and the current density. So the current density we get the I by A, which is the displacement current in our present case through the capacitor for an AC applied field, that is the field is varying with time. Now I also mentioned that the current here is a scalar quantity, but the current density is a vector quantity related by this expression. So in the previous AC circuit, if we consider the magnetic field lines about the current carrying conductor, then from Ampere's law we get the line integral value of the magnetic field about any closed loop is equal to the mu 0 times the total conduction current inside the loop, where mu 0 is the free space magnetic permeability. But when current passes through any dielectric medium, like through any capacitor as shown in this figure, that is the conduction current I, and this is the capacitor plates with charges like this, and if we consider some bound surfaces like 1, 2, 3 and 4, then we note that conduction current I passes through the surface 1, 2 and 4 only, but no conduction current completely passes through the bound surfaces 3 because it contains some vacuum region of the capacitor plate. So, here current passes through the surface 1, 2 and 4 but not through 3. So, for bound surface 3, Ampere's law fails for non-steady current. Thus, introducing the concept of displacement current inside the vacuum place of the surface 3, Maxwell modified Ampere's law for whole circuit is of the form where I discussed the ID is the displacement current related to epsilon naught del E by del T, that is the rate of change of electric field with time inside the capacitor plate. Therefore, displacement current removes the ambiguity of Ampere's law for any circuit. Now, for physical realization of the electric and magnetic field inside of a capacitor for varying electric field as shown in this figure, we may consider this static diagram at any instant of the AC voltage applied across the capacitor plate, where IC is the conduction current through any conductor and where the electric field that is perpendicular to the plates is varies sinusoidally, generating a magnetic field also perpendicular to the plane of this electric field, and this may be considered as the propagation of EM wave through the capacitor to continue the current in the circuit, and this current that is generating EM wave inside the capacitor plate in vacuum places is termed as a displacement current. Finally, we may also consider the following videos for the generation of electromagnetic wave or displacement current by AC current from a dipole antenna or capacitor along with the conduction and displacement current through vacuum.